Hello everyone, today we'll solve some more numerical problems based on Hamiltonian equations. Here your Hamiltonian is given as h is equal to p square q square. Here p is the generalized momenta and q is the generalized coordinate. So here you have to find p and q. Now you know that from the Hamiltonian equations that p dot is equal to minus del h over del q. So if you find from here del h over del q, then it comes out to be minus twice p square q. Let us say it is equation number 1. Similarly, you can find q dot. You know that q dot is equal to del h over del p. This is from the Hamiltonian equations, and let us say it is equal to twice p q square when we differentiate it with respect to p, and it is equation number 2. If we divide equation number 2 by equation number 1, then we can find that q dot upon p dot is equal to minus q upon p, or you can write it as dq over dt, and it will be dp over dt. So you can write it as dq over dp is equal to minus q upon p. Now you can have it as like minus dq upon q is equal to dp upon p. Now if you integrate it, then you can write it as minus log q is equal to log p plus minus log c, and the base for all the logs are e. Now it becomes that log p plus log q is equal to plus log c, or you can write this equation as that pq is equal to c, or you can say that p is equal to q upon c. Let us say it is equation number 3. Now if you see from equation number 2, you know that when you put p equal to q upon c, your q dot will be equal to twice c q. Because q dot you can write it as dq over dt, so it will be equal to twice qc. Now you can separate these, and so you can write it as dq over q is equal to twice c dt. Now if you integrate it, then you can find log q is equal to twice ct plus log c1, or you can write it as q upon c1 is equal to e to the power twice ct, or q is equal to c1 e to the power twice ct. If you put the value of q equal to c1 e to the power twice ct in equation number 3, then you can find p is equal to c upon q, and it will be c upon c1 e to the power minus twice ct. So you can find the value of p and q using the Hamiltonian equations. Similarly, here the Hamiltonian is given as x px minus y py minus x square by 2 plus y square by 2, and here at t equal to 0, x is equal to 1, y is equal to 1, px is equal to half, and py is equal to minus half. Now here we have the two Cartesian coordinates x and y, so here we will have the 4 Hamiltonian equations. Now we will find the value of the x, px, y and py, and what could be the relations between these coordinates we will see here. So we will write the first Hamiltonian equation, that is x dot will be equal to del h over del px. If we differentiate with respect to px, then we will see that it is equal to x. So here x dot is equal to x dot can be written as dx over dt, it is equal to x. Now separating the variables, dx over x will be equal to dt. When we integrate it, you know that it will be equal to log x base e equal to t plus c1. c1 is here constant of integration. So when t is 0, you know that x is equal to 1 is given, so c1 will be 0. If we put these values in earlier equation, log x base e is equal to t, so you can write it as that x is equal to e to the power t. Let us say it is equation number 1. Similarly, here you can find y dot, it will be equal to del h over del py, and from the earlier relation which you have given, that h is equal to this equation, x px minus y py minus x square by 2 plus y square by 2. Here, if you differentiate this equation with respect to y py, then you can find the value of y dot. So y dot will be here del h over del py, and this is equal to minus y. Now again, separating the variables, you can write it as dy upon dy is equal to minus dt, because y dot will be dy upon dt. Now integrating it, again your constant here will be 0, so y is equal to e to the power minus t. Let us say it is equation number 2. Now if we multiply equation number 1 and 2, then we can see that xy is equal to 1, which is the equation of a rectangular hyperbola. Now from the generalized momenta, we will see that what relation we can find out, because h is given as x px minus y py minus x square by 2 plus y square by 2. So p dot x will be equal to minus del h over del x. You know it from the Hamiltonian equations. So our relation will be minus px plus x. We can write this equation as p dot x plus px is equal to x. P dot x will be dpx over dt plus px is equal to x. Because x is equal to e to the power t, so we can write it as dpx over dt plus px is equal to e to the power t. Now if we multiply it by e to the power t, then we can write this expression as d over dt px e to the power t, and it will be equal to e to the power 2t, because e to the power t into e to the power t will be e to the power 2t. Now integrating it, we can have it as px e to the power t is equal to e to the power 2t divided by 2 plus constant of integration c2. Now when t is equal to 0, we know that px is equal to half. So here if we put t equal to 0 and px equal to half, then c2 is equal to 0. So finally our equation becomes px is equal to 1 by 2 e to the power t. Let us say it is equation number 4. Now similarly we can find for the y variable, p dot y will be equal to minus del h over del y. So p dot y will be equal to py minus y, and we can write this equation as p dot y minus py is equal to minus y, because y is equal to, so e to the power minus t. So this equation will be p dot y minus py is equal to minus e to the power minus t. Now if we multiply this equation by e to the power minus t on both sides, then we will have d over dt e to the power minus t into py is equal to minus e to the power minus twice t. Now integrating this equation, we will have this type of equation. If at t equal to 0, then py is equal to minus half. So here we will find now c3 is equal to minus 1. So this equation now becomes as py e to the power minus t is equal to 1 by 2 e to the power minus 2t minus 1, because c3 is equal to minus 1. Now as e to the power t is equal to px, so we can write this equation as py upon twice px is equal to 1 by 2 into 1 by, because e to the power t is equal to px, so it will be twice px whole square minus 1. Or we can solve it, then we will have the equation like this: 8px square plus 4px py minus 1 is equal to 0. Now you can see that this is not like the hyperbola equation, but if we put px is equal to half and py is also equal to half, then at t equal to 0 we will have that py is equal to 1 by 2 e to the power minus t, and px is again is equal to 1 by 2 e to the power t. So if we multiply px and py, then we will have a constant that will give you a rectangular hyperbola. Thank you. Hello everyone, today we will discuss the equivalence of the logic gates to NAND and NOR gates. For the NOT gate, you know that if the input is A, then after the NOT operation the output will be A bar. For the NAND gate, if the input is A and we apply the same input to the NAND gate, then you can see that here the output is same as in the NOT gate, because here it is your A input, so it will be A and it will be also A. So A into A after the AND operation will be A, but after the inversion it will become A into A bar, and this will become XY bar, so it will be X bar plus Y bar, or you can say that A bar plus A bar will be equal to A bar, or you can also say that A into A is equal to A, it will be equal to A bar. For the NOR gate, if the input is A and we apply the two same input to the OR gate, then you can see here that this input is A, this input is A, and this is your OR gate. So after it you will have the output A plus A, but after the inversion your output will be A plus A bar, because A plus A is equal to A, so here your output will be A bar. So in the first case you can see that one NOT gate is equivalent to one NAND gate and one NOR gate, because in all the three cases the output is same. Now we consider the second gate is AND gate. In AND gate, if we take two inputs A and B, then you know that after the AND operation your output will be AB. Now in the case of the NAND gate, here your inputs are A and B. So after the NAND operation, here your output will be AB bar, you know it, because after the AND operation your output will be here AB, and so NOT will make it AB bar. Now if we apply the same inputs AB bar to the this NAND gate, then you can find the output AB, because here this input will be your AB bar and this will also be AB bar. So AB bar into AB bar will be equal to AB bar, but NOT of it will make it AB double bar and it will be equal to AB. So here you can see that one AND gate is equal to two NAND gate. Similarly here this is your NOR gate and this is input A and this is input B. Now these two inputs are similar for the NOR gate, so your output here will be A bar because it is A, so A plus A will be A and the inversion of it will make it A bar. Similarly here it is B, so B plus B will be B and inversion of it will make it B bar. So to this NOR gate, the two inputs are A bar and B bar. So here your output will be A bar plus B bar. Note it is like X plus Y whole bar. So it will be equal to X bar into Y bar whole bar. So it will be equal to AB. It is like your here X bar plus Y bar. You know that X bar plus Y bar is equal to XY whole bar. Similarly here it will be AB whole bar and again the bar will make it AB. So here you can see that the one AND gate is equal to the two AND gate and three NOR gate. Now the third gate is the OR gate. Here you have the two inputs A and B. So in this case your output, you know it will be A plus B. Now this is your NAND gate. So if the inputs are same here for this NAND gate, then your output will be here A bar, you know it. Similarly for this NAND gate, your output will be B bar if the inputs are same. Now this is your third NAND gate. This is A bar and this is B bar. It has two inputs A bar and B bar. So output will be A bar B bar whole bar. Now it will make it is like X bar Y bar whole bar. So it will be equal to X bar bar plus Y bar bar and it will be equal to A plus B. So your output is same as in the case of the OR gate. So we can say here that one OR gate is equivalent to 3 NAND gate. Similarly here for the NOR gate, if the two inputs are A and B, so after the NOR operation your output will be A plus B whole bar. Now if the inputs are same for this NOR gate, then you will have the A plus B whole bar and again the bar, so it will make it A plus B, which is equal to the output of the OR gate. So here we can say again that one OR gate is equal to the 3 NAND gate and 2 NOR gate. Now in the fourth case we take the exclusive OR gate. You know that if there are two inputs A and B, then the output of the exclusive OR gate will be AB bar plus A bar B. Now here we use the NAND gate and it is 1-to-1 system. First we will have the one NAND gate, then we will have the two NAND gate and then one NAND gate. So it is also called as 1-to-1 system, and you will see here that we will have the same output here as in the one exclusive OR gate. So it is the first NAND gate and it has the two inputs A and B. So the output of this NAND gate will be AB whole bar. Now this output of the first NAND gate is applied here to this NAND gate and to this NAND gate. The other input for this NAND gate is A and for this NAND gate is B. Now this NAND gate and this NAND gate has two inputs. One is A and other is AB whole bar. Similarly, this NAND gate has the input B and the other input is AB whole bar. Now, when we do the NAND operation of these two inputs, then we will have A dot AB whole bar, and here we will have B dot AB bar, whole bar. So this value, if you check, it will be equal to, it is your like X, Y whole bar. So it will be equal to A bar plus AB double bar, or it will be equal to A bar plus AB. Similarly, this value will be equal to B bar plus AB. Now this NAND gate has the two inputs. One is A bar plus AB and other is B bar plus AB. So after the NAND operation, you will have the output here that will be equal to AB bar plus A bar B. Now we can check it that how we can have this output. This is your A bar plus AB. This is first input of this NAND gate, and the second is B bar plus AB. So after the NAND operation of these two inputs, you will have the output like this. Now you can write this A bar plus AB as A bar plus A and A bar plus B, and you can write it B bar plus AB as B bar plus A and B bar plus B whole bar. So A bar plus A, you know that it is equal to 1. So it will be here A bar plus B into B bar plus A whole bar, because B bar plus B is again 1. Now it is your like X and it is Y. So you can write it as A bar plus B whole bar plus B bar plus A whole bar. Now it is like your X plus Y whole bar. So it will be equal to X bar, Y bar. So you can write it as A bar B bar plus it will be B bar into A bar. So it becomes A B bar plus B A bar. Now you can see that it is having the same output as the exclusive OR gate. Now similarly, you can find the output as A B bar plus A bar B from the 5 NOR gates. This is your homework. Here you have to find the output for these 5 NOR gates as equal to A exclusive or B. Now similarly, in the fifth case, the exclusive NOR gate In case of the exclusive NOR gate, you know that your output is equal to AB plus A bar B bar. So here if you see that there are 5 NAND gates which will have the same output as the one exclusive OR gate, you have to check here your output. Similarly, here you can see that the 4 NOR gates will have the same output as the one exclusive OR gate. You have to do these outputs yourself. You have to find these outputs yourself. Try to find out these. Now we can make a table which you can learn that if you see from the earlier diagrams, you can remember that here from this table that one NOT gate is equal to the one AND gate and one NOR gate. Then one AND gate is equivalent to two NAND gate and three NOR gate. Then one OR gate is equivalent to three NAND gate and two NOR gate. One exclusive OR gate is equal to 4 NAND gate and 5 NOR gate. One exclusive NOR gate is equal to 5 NAND gate and 4 NOR gate. How you can remember it? You have to use. You can use the word NAOXXN. N for node, A for AND, O for OR, X for XOR gate, XN for XNOR gate. And you have to make for the NAND as 1, 2, 3, 4, 5. This is for NAND gate. Here 1, 2, 3, 4, 5. Now here 1 will be same, but 2 and 3 will be in opposite diagonals. Similarly 4 and 5 will be opposite diagonal for the NOR gate. So if here 1 AND gate, then there will be 2 NAND gate and 3 NOR gate. Similarly, if there is 1 OR gate, then there will be 3 NAND gate and 2 NOR gate. So you can make a diagonal here for the NAND and NOR gate. Similarly for XOR and XNOR gate, because you know that one XOR gate is equal to 4 NAND gate and 5 NOR gate, and one XNOR gate is equal to 5 NAND gate and 4 NOR gate. So you can again make here a diagonal, right? Similarly, you can prove that one NAND gate is equivalent to the 4 NAND gate, and similarly 4 NAND gate is equivalent to 1 NOR gate. So you have to remember this table. This will help you in solving the numerical problems where you have to find the number of the gates from the Boolean expressions. Thank you.